Thank you for being part of our study in engineering math. Lecture number 13 by Dr. William Emanuel. Partial differentiation. We have been studying lots of different things, and now we're looking at partial differentiation. A wild exponent function we have here, okay? You use differentiation, and it is not very effective. What we started with is still what we have. Okay, we would like to look at how do we differentiate? What is that all about? What is differentiation? Okay, differentiation, when we have d of x equal to delta of x, as we have here, d of x equals delta of x, because it is this exact number here of where it is, as it is no approximation going on here. We have straight from x1 to x2, we subtract the difference and we get an exact number. But when we go on the y, we're making a tangential line on this curve, and we're going to go into a little more detail in 3D. It's going to be very difficult to understand, but we're going to still do it. We see here that this is a tangential line, and this is an approximation of dy. Okay, so dy is not equal to the change in dy. As you can see, the change in dy is greater than dy. Okay, next we have here dy over dx is the rate of change of the f of x with respect to x. Okay, or we can call this the slope. Okay, when we deal with the dy over dx, we're dealing with the slope, what we remember in algebra. So we, again, let you know that dy equals the partial of dy. Approximate change for dy, and dy is not equal to the partial of dy. So what we would like to look at is, we want to look at f of x plus a very small change in x. A very small change in x minus our original function f of x equals to the change in what? In y of x. Okay, so we're going to go from here, and we're going to add this much of the delta. Okay, and now we're going to subtract that from this value here, which is where we are with f of x. Okay, and this will give us our delta of y. Okay, so we have our function adding what? We have our function, we add our delta. Okay, then we subtract from it what? Our f of x. Okay, here is our f of x, and we will get our delta of y. Okay, now let's look at this. D of y over dx. D of y over dx, the approximation, remember, is the limit as the change of x as it decreases and as it limits as it goes to 0. So, so d of y over d of x as it approaches 0 gives you close to the change in x of y over the change of x as the slope gets steeper and steeper. What if we want to extend this to n d's? Okay, in differentiation. Okay, let's look at partial differentiation. Okay, when we're looking here at partial differentiation, here's our function f at xy, and we're calling this z. Okay, so z is a function of x and a function of y. Along the AB curve here, x is what? Constant. Here's x. X is not changing. Z is changing. Z is going up. And y is changing. But x is staying the same. So, as we say, the partial of z, okay, over the partial of y is slope along AB. What is happening to x? Nothing. X is treated as a constant. When we are just taking a partial of z in respect to the partial of y. Okay, let's look at point P here. Let's take the partial of z again. Okay, this is the point P we're at. And we want to take the partial, at the partial of z, like we just did a few seconds ago. The partial of z, as z changes, it's going up and down. Okay. What does this tell us about the rate of change with respect to y, whereas in the y direction? So as we make this change, this is going to change as it is in the y direction. Okay, this is the y direction, this is the y direction, this is y. Okay, now let's look at this again as we look at CD. As we look here at CD, we see what is constant. Y is not changing. Okay, so we're taking a partial of z, of our function, as it relates to x. And we can see that x is changing. And where what? Y is treated as a what? Constant. It doesn't move. So then we can look at P in relationship to Z as a partial in respect to X. Tells us about the rate of change with respect to what? X. Whereas in the x direction. So as we can see, as we go from C to D, it's just changing in the x direction and also in the z direction. Okay, mechanically, take derivative treating y as a constant. Okay, so what I would like for you to do is, as this example, to find the partial of z in respect the function z, the partial in reference to x in terms of z. I want you to take the partial of z in terms of y. Okay, so we'll let you work that problem. Okay, as we can see here, if we take this in reference to x, the partial of z in reference to x, it's 2 comes down, this goes to the 1 power, so it's 2xy. Okay, you can understand that. And the same thing for z. Partial of z in respect to y, it's equal to y will just be 1, and we're just left with x squared. Okay, now let's look at, let z be f of x, as we said before. And so now we want to decrease some of the notation to make it a little easier to follow. Okay, we're going to take x, we're going to call x1 x, and we're going to call that f at 1. We're going to call y, instead of y, we're going to call it x of 2, and we're going to call this function f of 2. And then we're going to call z x at 3 with a function, or f at the function 3. So if we look here, we got the partial of z, okay, in respect to x. And we said we would say that that's also the function, okay, f. Okay, this is still a function f. Okay, and we're taking it in partial to what? X, as we did here, z. Okay, so now what we're looking at here is we're taking the function of x, of the function, the partial in respect to x, and what are we doing? Where y is remaining what? Constant. We talked about that earlier. Okay, that's one way to denote it. We can also denote it in reference to that we're taking z, and we have the x at the bottom, that we're taking a partial of z in respect to x. Or we're taking this function, which is still z, and we're taking it in respect to x. Okay, and now we have already told you that f at 1 is going to equal what? The x at 1, which is equal to x, f at x. So this here is letting us know that f of x and f at 1 is the same. That's what we're taking a partial in reference to for this function. So if we do the same thing for f at y, the function, and taking a partial in reference to y, we can have f at what? Y, or we can have f at 2, because we said that f at 2 is equal to, at 1, is equal to y. Okay, now we want to take multi-derivatives. Okay, so we have the partial of x, and we're having a partial of z, the function z, in reference to x. And so we have two x's on the bottom, and we have two partials on the top, so it's two partials in reference to of z in reference to, with respect to x squared. Then when we can take this also in reference to the partial, in reference to the partial of, in respect to y, and we're taking a partial of z in respect to x, and then we have the partial squared of z, we're taking it twice, of in respect to x, and the partial in respect to y. Okay, so now we can also do it for 3. So if we have x, we have z here, and we're going to take the double partial, the first partial in reference to y, and then we're going to take a partial, a double partial, one in respect to y and one in respect to x. So then we have 3 partials of z, and we're taking 2 in reference to y and 1 in reference to x. Okay, given this equation, we would like for you to take the partial of z with respect to x, the partial of z with respect to y, the partial of z twice in respect to x, and then the partial of z with respect to x and y. Okay, there's another practice problem. We're going to ask you to look at it in reference to angles and magnitude, r and theta. Okay, we're going to take this equation W, and we would like for you to take the derivative, the partial, as it relates to R, the magnitude, and as it relates to the magnitude twice, and then in reference to the angle. And that'll be what we call now we're going to move into total differentiation. We talked about this earlier already, if you remember this curve, and I said we would look at it in 3D. Okay, so if we look at PQR, okay, so on this we're seeing that P and Q is the actual curve itself, is the function itself. Okay, then this is the real value. Okay, this is the real function. Okay, now we're going to also look at it as it relates to PD, okay, which is our horizontal, okay, which we can look at as our x-axis, but when we look at the other one, we're going to look at it in XYZ, and that'll be our y-axis. So notice we have here, and then we're going to have z at P is equal to the same. It's not moving. Okay, now we're going to have it in reference to A. Okay, P of A is a tangential, okay, a tangent plane to the surface at P. Okay, so now we're going to look at this in 3 dimensions. It's going to get very difficult. Okay, so I'm trying to show you in 2 dimensions to make it easy. 3 dimensions, it gets very difficult. Okay, so we have here partial of x of the function f in terms of x, and the partial of x in terms of y. Our partial evaluated at P, okay, because we have our x and our y, and so we would like to look at this function, okay, in reference to that. Okay, now consider the YZ plane. That's what we're going to look at in a few seconds in our next graph. Okay, if we're looking at the YZ plane, what happens? We have AP, okay, right here. That tangential is what? The change in what? Of the function. The function changes, okay, as we relate to what? The partial of y and what? dy. So we see dy is not the change in y. It's not the same. We're using this because we're using this tangential. So this is only the magnitude of what? AP. That's all this is AP. Okay? And we're using an approximation here. Okay, so now we're going to look at another one that's a CF. We don't have that one in front of us. We're going to look at that on the other plane, where we're going to look at the partial of f in respect to x. Okay, so it'll be going this way. We're going to be looking at it. Okay, we have f of x, and before we looked at it in reference to, so now here is our dx. So as you can see, this is our dx, which is also equal to our change in x. So now what is going to be dz? This is going to be a 3-dimensional. Our dz is going to be our partial of x over, which we talked about here, okay? Our function is the partial of x dx plus, okay, plus the AP, the partial of x in this function, the partial of f in terms of y, and we're going to do dy, and this is a good approximation of the change in z when the dx and dy are small. So this is our dx, make this small, and make this small here, our dy. So here's our 3-dimensional image, which I was telling you about, which is very difficult to comprehend, but we're going to try it. Okay, we're looking here at P. We talked about PA, okay, there it is there. We talked about PQ. PQ is the function. Get that. PQ is the function that we was originally working with. Okay? Then remember, PA is what? Is nothing but a tangential. Okay? It's a tangent at P. That's what gives us our A. Okay? And we looked here before. We talked about CD. I believe it was C. All right. Well, we can. Okay. So here we have our change in our F function as it changes in reference to Y, our AD. Okay. And then as it changes here in reference to X, our function relates to X. These are the two functions that we were having, and we were adding them up. Okay. The same thing here. We have the partial of what? F in respect to Y, dy. You can see this is the same here. And then we have our partial, okay, of F in respect to X times dx. That's the same as this here, okay? This CF is the same as our GE. Our AD is the same as our BG. Okay, so now that we have these areas, this will give us, remember, this is nothing, this plane here is nothing but a tangential of P. That's all this is. So it's trying to approximate this. Remember that. Okay, so we have ER, okay, which is our change in our what? In Z. And we have EB, which is our approximation. This is our tangential. Okay, so this is the real value. Okay, ER is the real change in Z, and EB is the approximate. Remember that, the approximate. Okay, as Z gets smaller, the approximate level. And they said that if we added these two together, if we added this one, our GE and our BG, which is our function of F in respect to Y, and multiplied times dy, and we add it together with our function, partial of our function with respect to X and dx, we will get a close approximation to our true change in Z. Okay? We said over here, we have dz is equal to the partial of Z, same as F we said before, and the partial with respect to the partial of X times dx plus the partial of Z of in respect to Y dy. And these are the same functions that we have here, from B to G and G to E. Now, what about if we have infinite dimensions? Okay, we talked about one dimension, we talked about two dimensions. Now, if we have n dimensions, okay, if we have n dimensions, then we will do the same thing. We'll take Z, and remember we talked about the x1 and the x2 and the x3 and the x4 all the way to the xn, and we are going to multiply that times our d of x of n. Okay, so we have an example here we would like for you to practice. As you can see here, when we take the partial of x squared, we bring down the 2 and we leave the y squared. When we take the partial of y, we bring down the 3 and we keep the x squared, and we bring down, we reduce the y 1 power, which would be 2. Okay, So when we look at the dz, the partial of z, as in respect to x, dx, plus the partial of z, the partial of y, in respect to y, dy. Okay, we do it one more time. We have this. So now we're going to take this with respect to what? Dx. So we take this, we put it here, we just add a dx to it. We put this here, 3x squared, y squared. We're going to put that times dy, and we're taking 2x y cubed and multiplying that times dx. Okay, so find the total differential dw with, for the function e to the x y squared, the natural log of z. Now we're going to talk a little bit about the chain rule, now that you've had that example to work on. When we talk about the chain rule, what actually happens here? Okay, when we're looking at the chain rule, we're going to start with this specific example. Y is equal to the natural log of the sine and 2x. So let y equal the natural log of u. So we're going to substitute all of this, which is sine of 2x, and we just go write it the sine of v, and then we're going to take v and then we'll break it down into 2x. So what happens when we deal with the chain rule? The chain rule says that we have 2y over dx. We can break it up into dy over du, and du over dv, and dv over dx. And these will cancel here, the dv's and the du's, so that you can see this turns back into our original equation. So what is the partial, okay, of y, which we have here, okay? What is the partial of the natural log of u? It's 1 over u, okay? What is the, okay, so that's the first one. Now what is the second one here? Du over dv. What is the derivative of sine? It's cosine, okay? And we're going to do dv over dt. What is the derivative of 2x? Is 2. So we combine these together, okay? And we're going to place here for u is the sine of what? 2x. So we're going to place for u here, which is our derivative. I'm going to put this on the bottom. We have the sine of tu over the cosine of 2x, okay? So that takes care of that, and we bring the 2 out front. So what is the cosine of 2x over sine of 2x? It's the cot of 2x multiplied by 2. Okay, I know you thought this was going to be a very difficult problem. As you can see, when you break it down, it's much simpler. Let's extend this work with partial differentials. Okay, so we're going to start with the total differential. Okay, we have dz, and we have the partial of z over, in respect to the partial of x, times dx, plus the partial of z in respect to the partial of x times, dy times dy. Okay, so the first thing we would like to do is we want to divide by dt. So if we divide everything by dt, we have dz over dt equals the partial of z in respect to the partial of x times dx over dt, plus we have the partial of z in respect to the partial of y, and we have dy over dt. So in general form, for n dimensions, okay, we're going to do the same thing. And the only difference is our dz over our dt equals the partial of dz in respect to x1, okay, then x1, which is x2, x3, x4, which is xi as it increases to n, and we have the same thing with the dx of I, the derivative of x of I in respect to dt. So we looked at this earlier. We had 3 dimensions and we just added 2 of them. We added the y and the x, so we were able to come up with the z. So now we can take it to n dimensions. Okay, and as we said, taking this by itself would be difficult. So we break it down and it becomes very useful for differentiations. Okay, so we have an example here where you have find dz over dt if z is equal to x over y and x is equal to the sine of t and y is equal to the cosine of t. Okay, and we'd like for you to practice another problem, problem number 3, using the chain rule this time to find the dy over dt for y equal to u squared v, and then for u equals the square root of 2t, and for v equals the sine of t. Okay, implicit differentiation. Now, so now we're moving to another way of differentiation that'll be useful to us. Alternatively, we can use total differentiations. Okay, this is useful for finding difficult derivatives, which we have seen already. Example, find dy in respect to dx and the derivatives, second derivative of the function y over in respect to x squared. If y equals y squared plus y equals x. We'd like for you to work that problem. Okay, now when we look also, we have another practice problem for you. Okay, find dy over dt if ty plus the natural log of y equals t squared. Thank you very much for being part of this study. So, I see you have a lot of practice problems to work. So, you knock it out and we will discuss them in class. And obviously, in class, I'm going to have a lot of problem solving in class today. Thank you and enjoy your day.